All right, guys, when we last left our intrepid heroes, they were doing this problem. If you skipped ahead in the video, this is, I basically finished. I did the entire problem basically by taking the two sets of variables and split it up going up and going down, and I explained all that. I'm not going to do it again right here. The purpose of this video is to look at how you could take this problem and just do it with one set of variables. We know we can do it with one set of variables because it stays at the exact same acceleration the entire time. So we do not have to split up the sets of variables like we might have to in a problem like a car traveling down the road and hitting the brakes. So this problem would be useful when there is, for example, a constant acceleration, specifically if there is some sort of velocity and you need displacement and it's going to happen a couple times. You'll see what I mean as we continue here. All right, so let's get rid of this extra work that we don't need. And let's say, instead of looking at it when it's going up and when it's going down, I'm going to erase over here and say, let's look at the whole path. Now, when we did split it up, what we were saying is by splitting it up, going up, we were looking at the section here to here. And we basically made that the section by saying that the velocity final was 0. We're telling kind of the math, the problem, whatever, that's what the section we want to look at, and that's how we did it. Okay? And then on the way back down, we set our initial position here and our final position there. Since we are doing the entire path, okay, so 22 meters per second, this path is going to go up, it's going to go down. That means, my marker's not great, that this right there is our initial position. And this is our final position. I'm looking right now, by the way, at exactly the time part of this. If you're curious about the total distance part, that was in the last video, and you can check that out. So we're just looking at how to find the time. Now, if this is my initial position, and this is my, also, apologies, there were a couple times that were asked for. The first time that was asked is for when the mug goes up and comes back and goes to the same location. Okay. The second one was asked if it goes up and comes down and hits the ground, and I'll address both of those here. Okay, so let's come back over here. Let's erase the variables and say, once I've established this is my initial position and this is my final position, okay, then I can start to figure out what these are. The initial velocity, well, what's the speed right here? Still that 22 meters per second. What's the final velocity? Well, where's the final velocity for this segment? Since this is my final spot, that's my final velocity, and I don't know it. Okay, acceleration. Acceleration the entire time is negative g. This time, since we're doing the entire segment, shouldn't need to be added to anything. It will be the total final answer, and it will get to be the exact same answer as if you had done it the previous way. Displacement. I'll remind you, displacement is specifically a straight line arrow, regardless of where it goes, from the beginning to the final. So, in this case, even though the mug goes up, the mug comes back down, the displacement is a straight line arrow from here to there. So that would mean that the displacement is in fact negative 4 meters. As a matter of fact, the only thing that's going to change here, I know I was going to show you both of these, if it comes back to the hand, is the displacement in that case is in fact 0. Now, let's talk about this math, okay? If you go straight for the time, you have to use this equation. Okay, there is a workaround to start with. I'm going to tell you the workaround because I want to make sure that if you're doing a test or if you're doing a quiz and you're under a lot of pressure, that you know that you don't have to do it this last way right now, but it's coming, okay? So I wouldn't avoid it forever. There are problems where you can't avoid this at all. You have to do it this particular way. But the workaround is real simple. Basically, this is what we would have to find if we go straight for time. The workaround is don't go straight for time. Find the final velocity first. If you find the final velocity first, you would do this. You would use vf squared equals vi squared plus 2a delta x. And then once you have the final velocity, you can plug in anything. I think the easy one to use is this guy right there. Now, we are not going to do kind of the workaround. We're going to go straight to this guy right here. Now, for starters, if you go back to the initial position and the displacement is 0, here's what would happen. This would go to 0. And actually, now you've got a 0, a time, and a time. So I can actually now divide by time to cancel out 1. And I'd be left with this. 0 is equal to VI plus 1/2 A delta T. That's because I divided by delta T. I could not have divided by delta T if this doesn't cancel to 0, because then I'd be left with the delta X over delta T, and life would be even more complicated. But specifically, since it is 0, 0 divided by delta T is still 0. From here, you can do some pretty basic algebra. You can subtract this over, and then divide by 1/2 A, or as we discussed before, you could multiply by 2, divide by A, and that would get you the delta T. Not too hard if it is 0. But that's not what we wanted to get. What if it's not? What if it's that -4? Well, then we have to go back up here. Like I said a second ago, we can no longer divide by delta T, because that's going to make the problem more complicated by giving us a delta X over delta T. What you're going to see here is that we have, I know acceleration, so we have some constant times a variable squared. We have another constant, which we know, times a variable to the first, and we have a third constant here that doesn't have the variable at all, or arguably has delta T to the 0, because anything to the 0 is 1. This sounds remarkably like this setup right here. Quadratic equation. So the quadratic equation is in fact how you answer this particular problem. So let's show you how you specifically use it. Okay. For starters, how does this guy match to this? Well, like I said, the A is whatever's multiplied to the variable squared. So let's go ahead and rearrange this. Let's start with this guy right here. This is 1/2 A. So this A, by the way, is not acceleration. This is just that constant. So actually 1/2 A is A. I know that's confusing. I apologize. Times delta T squared. So this is that constant times the variable squared. Then we have the variable times x to the first, which is right here. So we plus VI, that VI is my B term, times my variable to the first. The last piece of this is you'll notice this format has all of the constants on one side and the 0 on the other. So what that means is I did not start with that. There's an equal sign here. So I'm going to move this to the other side by subtracting delta x on both sides so that it can be equal to 0 here at the very end. And this negative delta x, that's my C term right here. Now I can go ahead and plug into what's known as the quadratic equation. Negative b plus or minus the square root of b squared minus 4ac all over 2a. Now, I usually like variables, and if you were trying to solve for delta t, variables are exactly what you'd have to plug in here. But let's go ahead and figure out what these numbers are so that we can make it a little bit easier. Okay, this is 1/2 a. Now, a, be careful, is in fact negative g over there. So my a term is negative g over 2, which is negative 4.9 meters per second squared. B is my velocity initial. My velocity initial is a positive 22 meters per second. And C is the negative displacement. The displacement is already negative, so those two negatives are going to cancel for 4 meters. Now that I have these, I'm just going to go ahead and plug that in. Negative B, so negative 22 meters per second, plus or minus the square root of B squared, 22 meters per second squared. Notice me, by the way, putting in units anytime I write a number. So negative 4 times A is that negative 4.9 meters per second squared, times C, that positive 4 meters. And that's all over 2 times A, where a is negative 4.9 meters per second squared. So the quadratic spits out two answers because of the plus or minus right here. So what I like to do to make my life as easy as possible is I do this piece first. So 22 squared equals minus 4 times negative 4.9 times 4. Square root that. So everything underneath here is 23.7. 71. Let's go 7 meters per second. Now, I'm going to get two answers by adding and subtracting, so I would just do each of those separately. Now, I will tell you in this particular case, one of the answers is in fact negative, which you can kind of see ahead of time. And you can see that, excuse me, ahead of time because we know the bottom is going to be negative. So if the top ended up as positive, that's going to give us a negative answer. And that will happen actually if I take negative 22 and add 23, since 23 is bigger. If you get the negative answer, that just means that's not the one that you're looking for. Cancel that out. Or in this case, so I'm going to subtract. So I get negative 22 minus 23.7. Okay, divided by 2 times this for an answer of what we expected already, 4.66 seconds. Again, the quadratic, it's not an easy thing. And I know that some of you are going to look at this and go, it seems way more complicated than the other way. Well, that's why I showed you at the beginning the trick that you could do to do this instead. I will actually share with you in another video why that trick is exactly the same thing as what we just did. I'll do that here in a second.